Alright, welcome everybody to week 9, day 1 on the 9th of March, 21. We're going to do today something I've been putting off for a while, which is going over octal and hex numbers. Shouldn't take too long, but they are kind of important. You've probably seen numbers like this before: 0x, 9, CC, FA, 10, something like that. That's a line through it so you know it's a 0, not an O. You guys seen this before, like when we're working with pointers and stuff like that? Pointers are typically printed in hex. The reason for that is because every hex digit is really 4 binary numbers together. So 9 is 1001, right? So it's a lot more compact to write a number in hex than it is to write it in binary. Okay, and so what is hex? Hex is what's called base 16, which means that every digit goes from 0 to 15. What we're used to is base 10, right? The numbers go from 0 to 9. And we're also used to base 2, which is called binary, right? You got numbers from 0 to 1. Huge swapping range there. So the reason why we use hex a lot is anytime we want to represent binary numbers and we don't want to type like 64 numbers in a row, it's kind of annoying. We use hex instead. Skyrim console commands are in hex, yeah. GDB uses hex, yeah. It's very common, and basically anytime we're not dealing with like a number, but like with a bit pattern, we use hex usually. It's just more concise, more compact. In C++, you can now write 0b, 011, 0111, 0. That prefix there means binary number, and so you can do that now. That actually is a somewhat recent addition. This, though, is the classic. It's been around since, I don't know, forever. And so what you do, if you want to enter a hex number, you type 0x first. This doesn't mean 0 times the number. It doesn't mean we're multiplying this number by 0. No, it's just this. If you type this prefix in, then C++ knows you're talking about a hex number and not a normal number, right? Because you could have hex 10, which is different from binary 10, which is 0b10, which is different from decimal 10. Right, these are 3 different numbers, right? So that's just 10, This is 2, right? 0b10 is the number 2. And 0x10 is 16. So if you don't have any prefix at all, then it is decimal. Your normal number is if there's no prefix. If you have a prefix of 0x, that means it is hex. Hexadecimal. And if you have a 0b prefix, that means it is binary. Okay. And if you have a 0 prefix, like for example, if you write 033, that 0 prefix means it is an octal, which is base. So an octal numbers range from 0 to 7. And it just is 0 before a number will make it octal. This bites a lot of new computer science people a lot, because like they'll do things like say, int x equals 03. Like if they have a bunch of numbers and they're like trying to line them up and have like everything be 2 digits, sometimes they'll type 03, and that will make it an octal number. In that case, octal 3 is the same as regular 3, so it's not a big deal. But if you were to write, like if you're trying to make everything 3 digits, int x equals 100, and int y equals 00, let's say 030, this is not 30, because you have that 0 prefix there. That is 28, right? So if you try, like some people try doing that so that just everything has 3 digits, that will be octal 30. Not maybe the best prefix in the world. That was a decision made a million years ago. So It is what it is. Okay. YX. Hex. 0x is hex. Yeah. That's how you know it's a hex number. 0x. It's a hex. Okay, so what are the 16 numbers possible in hex? Well, you've got your normal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is A. 11 is B. C is 12. D is 13. E is 14. And F is 15. Okay. So O looks like the O, which is the first letter in octal. Yeah, but if they made it like an O, I don't know. Like, because people will do octal by accident, and to me that's kind of iffy language design, you know? Like if you have people making the wrong number by accident. Kind of like I don't like this. If you do something like this, question mark, exclamation mark, question mark, this gets parsed not as you would think. Like even if you put this within a string, this gets parsed as something called a trigraph, which thankfully has been removed from C++ now. But this was a way of typing in characters that weren't on your keyboard back in the 1970s when keyboards didn't have things like I don't know, dollar signs or I don't know, ampersand, things like that. So IBM fought the removal of trigraphs for years. I don't know why. Probably because they had some code that used trigraphs in it somewhere and they didn't want to refactor their code. Yeah, anytime you find like multiple question marks, you know, together, like it would get parsed. The three characters get parsed as a trigraph is a bizarre and stupid system. It should have been eliminated a long ass time ago because people type it by accident, you know. Oops, accidental octal, yeah, accidental trigraphs too. Okay, so let's take a look at this. So let's say I have in hex F F F F 0 0 0 0. Okay, so me as a computer science person, a veritable master of computer science, as you will, when I look at this bit pattern here, I'm like, okay, that's all ones and that's all zeros. That's how the computer science mind works when looking at hex numbers. Like I can just look at this and be like, all right, see, F is 15, right? And 15 is 8 plus 4 plus 2 plus 1. Yeah, 15. Okay. And so this is the same thing as writing 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0. So this is a 32-bit number, and I only need 8 characters to represent. That is why we use hex. Okay. So let's give a slightly more complicated example. You know, maxent would be F, 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 8. If this was an unsigned integer, this is the maximum integer, all ones, right? What is this number if this was a signed integer? What value is this if this was a signed integer? It's all ones. And remember, 2's complement? What is all ones in 2's complement? Can you use hex in assembly? Yeah. Mm-hmm. Sure. Yeah, all ones is -1. Okay. So the maximum signed integer is 7. F F F F F F F F F F F F. Okay. Why 7? Because 7 is 0 1 1 1. Right? So remember the top bit is the negative, was it negative 4 billion bit or 2 billion bit, whatever it is. And so with that off and all ones remaining, that is the maximum positive integer for a int. Okay. So, yeah, you'll even see that. Like, let's go onto the server. Sports. Okay. So that is in decimal? Yeah, it's in decimal. Let's not make it in decimal. Let's make it in hex. There we go. It's in hex now. Cool. So the memory address of Muya is bed C09E0. So I know it's pretty close to the top of memory. It's an unsigned integer. So yeah, it's pretty close to the top of memory. Yeah. And so, you know, being able to, you know, just kind of look at a hex number and understand what it means is pretty normal. If we nude something, then main.cc. What if we nude to memory? Sports ball pointer Rivera. It goes 1 through 9, then 8th ref. That is correct. Yeah, equals new sports ball. Passing in 20 for the age. The team is going to be team R for Team Rocket. The name is the other team. There's 2 teams. Well, that'll be Team Rocket as well. And the starting score will be 10, because why not? Okay, so if we see out Rivera, that's a pointer, right? Pointers are just memory addresses. So when you new memory, it's going to allocate enough memory to hold 1 sports ball. And the start of that block of memory will be held here. Remember, pointers are just integers. And so if we see out it, it's just going to tell us what memory address Rivera is at. Okay. And so you can see that B, so Muya is now at B. Let's see, it's different every time, right? And then Rivera is at memory address not very high at all. There, you see how there's only 7 digits there, whereas that has 8. So a 32-bit address has 8 digits, right, in hex. This is only 7. So there's actually a 0 in front of that. So you can see that the data segment is way down below. The stack's up here, data segment's down here. Stack grows downwards, data segment grows upwards. If we were to allocate another one, let's do Tran, we'll be on team T. So 100 points. And we will see that Tran's memory address is higher than Rivera's. Remember, the data segment grows upwards and the stack grows downwards. Now, this isn't necessarily given because the way that the memory allocator works is somewhat opaque, right? Like if it had found some deallocated block of memory down lower, it would reuse that. So there's no guarantee that, you know, it's not monotonically increasing, right? If you're newing and deleting stuff, the memory manager will be like, oh, there's a chunk of memory down here that's unallocated, and it fits this really well, so we'll plug it in. Okay. So Yeah, and so you can see that trans address is 38 higher than Ribera's. And if we do it again, but it's not 38, it's 38 hex. It's 38 in hex. And so each digit in hex, right, you see how that's 9 minus 6 is 3, 8 minus 0 is... So it's 38 higher in hex. So each digit in hex, right? So what does it mean? In binary, like if we have 0, 1, 1, 0, this is the 1's digit, the 2's digit, the 4's digit, the 8's digit, right? In decimal, if I have 720, this is the 1's digit, the 10's digit, the 100's digit, right? 10 to the 0th, 10 to the 1st, 10 to the 2nd. In binary, 2 to the 0th, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, right? In octal, octal 420, that's the 1's digit, the 8's digit, the 64's digit. In hex 38, which is the number we're interested in here, it's the 1's digit and the 16's digit. So this is 48 plus 8. So 16 times 3 is 48. 48 plus 8 is 56. So Mistran's memory address is actually allocated 56 bytes higher than Ribera's. And again, there's no necessarily any rhyme or reason to it. We do know that it has to be bigger than the size of a sports ball. CC. And so if we see out the size of a sports ball, we will get a number. And so we know that trans address will be at least that big past it. And I believe we could do the alignment. Align of, yeah. Okay, so we can see that sports ball is 48 bytes big, and it's aligned on an 8-byte boundary. The reason why it's aligned on an 8-byte boundary is because it contains a double in it. Doubles are 8 bytes. If I were to change this to be a float, and maybe this string might mess it up too. Well, let's try that. Let's try making a float. Yeah, so if I change the double to a float, then the alignment of the struct changes to 4 bytes. In other words, if you had an array of sports balls, they would have to be on a multiple of 4, whereas before they would have to be on a multiple of 8 because they had a double element inside of them. And so the size of the sports ball actually dropped from 48 bytes to 40 bytes. Why? Why? Why did it change? Why did the sports ball size go down from 48 to 40? Should have gone down to 44, right? A double is 8 bytes, a float is 4. Why did it go down 8 bytes? Monotonically increasing, yeah. You thought you'd never hear that again, right? So why did this save us 8 bytes instead of 4 bytes, right? Doubles are 8, floats are 4. It should have reduced the memory size of it by 4. Right, but it reduced it by 8. Why? Initial offset, memory alignment? Yeah, it's a memory alignment thing, right? And so it will pad elements. It'll waste memory if they are not set up right. Like if I were to reorder these two elements here, so it goes float and then it's string, and the string's probably just a pointer behind the scenes, and then we have the two chars next to each other. In fact, let's put the int here and then finish with the two teams. We can get the offsets in a second. So if I compile that and run that, cannot convert. Shoot, all the order is different now. Huh? Maybe that's age equals 20. I can do that in C. Yeah, it might just be a C thing. All right, so age is still 20. Name is going to be Ribera. $10 is the score. Team Rocket. Let's put Tran back in here. So there we go, and we can see that the memory usage of this struct dropped to 36 from 40. All I did was reorder the things, and the actual the memory imprint, the memory footprint, the amount of memory consumed by the struct actually went down. And this is considered the lost art of struct packing, which is to actually consider this when you're making your struct, because I mean it's free, so why not? You know, but what you want to do is have all of the elements of the same size together, right? Because remember, if you have a char up here, then it has to align, you know, to a. It'll waste space because the next thing has to be on a 4-byte boundary. So if you have a char there, then you're gonna have 3 bytes of wasted space. And so you want all your chars kind of together, all your floats together, all your ints together, and that'll tend to use less RAM. And if we were to look at the offsets now, just put these in order so it's a little more sensible. So Muya is still way up high in memory because he's stack allocated. Offset of age is 0. Offset of name is 4 bytes later because age is 4 bytes, right? It's a float. Name is a string. So it looks like that string is eating up 24 bytes. Probably, I don't know, a size, a couple pointers, I don't know. Some stuff going on inside of the string class. And then the score is an int. And so an int's 4 bytes. And so team 2 starts 4 bytes later. And then team 1 starts 1 byte after that because it's a char. So it's a char following a char, so you don't waste any memory that way. So we can see here that Tran is 28 in hex, 28 hex past Ribera. So if you're ever confused about this kind of stuff, you can come over into programmer mode, into your favorite graphing calculator, and I can click on hex mode, and I'm going to type in 28 because Tran is 28 in hex past Ribera. And so you can see in decimal that is 40 bytes past. Okay. So even though every sports ball is 36 bytes, the new actually put Tran 40 bytes past. And let's try this again. Let's see if it's consistent. Looks like it. It's always 40 bytes after. Okay. Again, there's no real consistency to it. Just know that, you know, unless we're deleting things, she'll be above Ribera, and the memory usage on the heap grows upwards. So if we do one more student, let's add Debello. Debello is, of course, 200 years old. And you will see that Debello is higher in memory than Tran. So how much higher is Debello than Tran? Tran is 488. Debello is 4B0. Can you guys figure that out in your head? What number is B? A is 10, so B is what? A is 10, B is what? 11, yeah. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Okay, so how many bytes higher is Debella than Tran? Well, we can subtract 4B0 minus 488. Let's do this over here. So we can subtract 4B0 minus 488, and math works the same way. So when you subtract 8 from 0, you got to borrow 1 from this guy, right? So we'll turn B into an A and borrow a 1. 10 minus 8 is 2. A minus 8 is what? What is A? A is 10, right? So 10 minus 8 is 2. And so the answer is hex 22, which is 32 plus 2, 34 bytes. Okay. So right? I don't know if that's enough room. 4B, hex please. 4B0 minus, no, clear, thank you. 4B0 minus 488 is 28. What did I do wrong? Did I write 2? Why did I write 2? Because that's a 16, that's why. Boom. Yes, thank you. That's a 16 because it's 10 hex. Not a 2. 16 minus 8 is 8. I knew it was wrong because the difference in memory was smaller than the size of a sports ball. So always double check your mental math. Okay, yeah, I borrowed 16, right, not 10. Okay, so 4B0 minus 488 is 28 in hex. 28 in hex is 40 bytes. Okay. And so the students are all spaced 40 bytes apart by the memory allocator. Again, there's no real guarantee of any of this stuff. It's just how it is. There's always a possibility that if you turn on the optimizer, it'll change things. Yeah, look at that. That's a 6-digit number. So it actually is noticeably lower in memory now, right? You see that? Even still, these are laid out 28 hex apart from each other. So they're still 40 bytes apart from each other. But it's much lower. Like the data segment's actually much closer to 0 this time, which is interesting to me. Okay. So are we going to have a hex worksheet? It'd be cool to get better at reading hex. Yeah, sure. We can do a hex worksheet. I don't have one right now. I can make one for you. Yep. Hex only hard because monkey brains are like base 10. Yeah. The thing is, like, if I give you a hex worksheet, like, you can just type it all in, and I kind of want you guys to develop the intuition for hex. So what else? Okay, so converting to and from hex. It's pretty easy. So if I gave you this number here, 101 is binary, right? 0B. 1010 0111. Convert this to hex. So if you were to convert this to decimal, it's kind of annoying, right? Because you have to go like, okay, that's a 1, that's a 2, that's a 4, 8, 16, 32, 64, 128. And so to convert decimal to binary and decimal to hex is annoying. It's annoying. So this would be 128 plus 32 plus 4 plus 2 plus 1. So 167, right? Kind of annoying. Converting this to hex, though, is easy. So what you do when you're converting to and from hex is you look at the binary numbers in groups of 4. So what is 1010? What is 1010? In binary, let's say. What number is 1010? 2? No, it's not 2. How could it be 2? 1010 is greater than 10. You're right, it's 10. 1010 equals 10. This is one of the moments when my wife walks in and just goes, nope. It just walks out. 1010 equals 10. No. No. It's like when I'm explaining modular division. 6 divided by 2 is 7. Nope. 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 Not going to do that. So what number in hex is 10? What number in hex is 10? If we're converting this group of 4 bits here to hex, what you do when you convert binary to hex, it's really easy. 10 is the letter A, correct? And then 0111 is 7. So what is 7 in hex? What digit is that in hex? 7, yeah. So 0B, 1010, 011 is the same as hex A7. Okay. So converting from binary to hex and hex to binary is really easy. I was actually tasked with writing a program to do that back in the day, professionally. Actually, the first place I worked at, they needed a hex converter, and it was like 4 o'clock. It's about ready to go home. They're like, "This is an emergency. Can you write a hex converter for us? It looks really complicated. We don't understand it. We need it now." And I was like, "All right, I'll see what I can do." I had it done in 15 minutes. It's like, it's pretty easy. Okay, so yeah, so if I told you hex A7, convert it to binary, what you do is you take each digit one at a time and convert it into a group of four binary numbers. Okay. So that's it. That's all I had to do. So yeah, it's pretty easy. So let me give you let's do a little thing. All right. So what is 0F A? Convert this to binary, please. I just went to the dentist. Still have fluoride in my mouth. Let's see how this coffee tastes. It's a chai latte. That's how this tastes. Not bad. Yeah, you can put spaces between the numbers or not. I don't really care. You can prefix it with... no, it's not the fluoride. I'd already cleared the fluoride off, but it just melted. So it's very watery. So you could write this as 0B, 1111, 1010 if you want. Or you can ignore the 0B. It's fine. Just put spaces between them. Or no spaces. Either way. It's all good. Looks like you guys all got that. Alright, let's do the other way. Let's do a quiz for you guys. What is 1001 1101? This is binary. Convert to hex. Or grab 4 bits at a time. Each 4 bits turns into 1 hex number, 1 hex digit. Our sea shanties will be this Friday, 4 o'clock on Discord. Bring your pirate outfits. sea shanties weren't actually sung by pirates. It's a complete anachronism. The golden age of piracy was like in the 1600s, you know, around there. Kind of extending and kind of, you know, there were pirates. Jean Lafitte was through the 1800s, actually, early 1800s. When did he die? He must have died in like 1830, something like that. Did Jean Lafitte die? $1820. That's right. Close enough. Okay, so yeah, sea shanties are work songs from the 1800s. So I guess technically Jean Lafitte could have sung a sea shanty. Most pirates were like way earlier. Yeah, so this is 8, that's 1, so that is 9, and this is 8 plus 2 plus 1, which sounds to me like 11. 11 is, 8 plus 4 plus 1, which is 13. 13 is D. Okay. So the answer is 0x9D. Or you don't need the 0x. It's fine. Your black flag poster says different. Yeah, black flag has ships that can full sail directly into the wind. They got like a outboard motor or something. Add more sails. Wind's blowing directly at you. Okay, let's go faster. We put more sails down with the wind blowing at you. A square map. No. Black flag is not a structurally accurate game. Does have some pretty good sea shanties in it, though. Like, to be fair, does have some pretty amazing sea shanties in it. Okay. But, yeah, the pirate music and sea shanty music are different. Okay, let's do a couple more. Let's convert 0x E4 to binary. That is an E. Let's clean that up a little bit. What is 0x E4 in binary? Yeah, sea shanties were work songs. They weren't sung by Navy ships, also mostly. Although there is some evidence of some sea shanties being sung on a military vessel, they're almost all merchant vessels. Kerbal Pirate Program, add more sails. Peak of accuracy. Yeah. Valheim actually has reasonably good sailing. The rigging makes no sense on the Valheim small boat. Like the ropes, the way the ropes are rigged on that ship makes really no sense at all whatsoever. But you know, the way that at least, you know, you can't sail directly into the wind, but you have to tack. Like it's pretty good. All right, so E is 1 less than F, right? F is 1 1 1 1, so 1 less than F is 1 1 1 0. So this is 1 1 1 0, and 4 is of course 0 1 0 0. So yeah, the answer is 1 1 1 0 0 1 1 0 1 0 0, which all y'all got. Okay. I guess we do one more, and that is hex to decimal. Not hexadecimal, hex to decimal. And so let's say 0 A7. What is that in decimal? This is the 1s digit. This is the 16s digit. Sixteen times 10 is 160, plus 1 times 7 is 167. Yep. All right. What is F? You'll see a lot of Fs a lot of times when you're doing bit masking. If you're doing ands and ors and things like that. If you and something with a bunch of Fs in a row, that's going to leave those bits untouched. So if you were to and something with FFFF0000, then the upper 16 bits would be left untouched. The lower 16 bits would be cleared. So you'll see Fs and zeros a lot when dealing with like bit patterns and bit masking and things like that. So FF is the maximum value for a unsigned 8-bit char. So if you're dealing with a unsigned 8-bit, then this is indeed 255. But if this is a normal signed char, if you just have like a char C is equal to 0xFF, then this is equal to negative 128. Okay, I didn't tell you what type, so either is acceptable. So when you're working on your homework, the homework is all unsigned 8-bit chars. So 255 is, yeah. So if you want to set something to 255, set it to FF, right? If you're working with normal integers, though, this would be, sorry, negative 1, my bad. All right, sorry about that. That's negative 1, right? If you're doing with sign numbers. All ones is negative 1 and 2's complement. Okay, so let's talk about the homework. Do you guys have any other questions about hex? I mean, in all honesty, if I were to ask you to do something like, if I were to ask you to like convert 167,5,3,2,1 to hex, I'd be like, bro, really? Yeah. Easiest way of doing this is to convert it to binary first. So convert that to binary, and then convert binary to hex. That's how I would do it. It's kind of annoying to do it directly, but what I'd really do is be like, yeah, sure, okay. 1657321, and hex is 199,039. That's how, like, yeah. It's really easy to go back and forth between hex and binary. Going back and forth between decimal and hex is kind of annoying. It's kind of annoying. Okay, so Octal's not really used that much. You'll see it in file permissions. File permissions in Unix are in Octal. Octal is groups of 3 bits. So Octal digits would be like something like this. So in Octal, this would be 0, what is that, 3, 6. You guys see that? So Octal is groups of 3 bits at a time. Hex is 4 bits at a time. Pretty much everything we do these days is a power of 2, right? 8-bit system, 16-bit system, 32-bit system, 64-bit system. They're rarely divisible by 3. Like we don't usually do groups of 3 with binary numbers, and so Octal, yeah, I mean, you got to know it, I guess. Like I said, if you use chmod to set permissions, it takes an octal number. I mean, it'll pop up here and there, and so when you set file name, when you set permissions on a file, so if you come over here and say ls-l. ls-l gives you detailed information on a file. You can see it's 1400 bytes. If I make it human readable with an H flag there, see it's 1.4K, which is really weird because main.cc is only, wow, it is kind of big. Okay, all right. I've typed over 1,000 letters in it. Look at me. Check me out. How's it 211 lines? Really? Oh, that's word count. Yeah, it is 39 lines, 200 words, and 1,400 characters. Yeah, okay, so it's over a K in size. Cool. Go me. Over here, though, so have you guys ever done this before in ls-l? Have you guys ever done that in Unix? In a Unix system? For those of you that haven't, you should take the effort to learn Unix. I'm going to propose a Unix class here at the college. It should be really nice because Unix is cool. Unix. My Unix lab, CSE80 at UC San Diego, was hands down my favorite class. It was just us one night a week, late at night on a Wednesday night, going into this dark computer room. There's like this throne. It was like an elevated stage. And so we're like sitting down here, and like up on this throne, there's this old wizard, Unix wizard, and he'd just sit there and do Unix wizard stuff. And so for just 2 hours, we just sit there and learn about piping things and shell scripting and all this kind of stuff. It was a cool class. So yeah, if you do -LA, that will show you all the hidden files, which I'm only showing one here. That you can see I got any file that starts with a dot in Unix is invisible by default. So anyhow, so this is the owner of the file. This is the group of the file. So you can give permissions to your group, like your class, for example. This is the size. This is the last time it was modified. That's the file name. It is colored. Everything that's marked executable is colored green. Every directory is blue or kind of periwinkle. And regular files are white. Over to the left here, though, is what I'm trying to show you, which is that file permissions are held in Octal. And so they're in groups of 3 bits. And so if a bit is set, you have permission. If it's not set, you don't have permission. So for example, if any of you guys tried reading the PWM demo, which we would be doing if we were doing Raspberry Pi stuff, which we're not, unfortunately, but PWM can control an LED to make it glow brighter or dimmer. If any of you tried reading this file, you would not be able to. Why? Because I have not given you permissions. If, however, I wish to be nice, say chmod, people in my group can read PWM demo. Then when I do this again and scroll up, you can see that the second set of 3 bits is for your group. However, my group is just me, so that still doesn't help you. And so if I were to come back up here and say other people, in other words, anybody other than myself, or if you want, you can say all, and that would be user and group and others. I'll just say others for simplicity. So that means you guys, you can now read pwm.c. So if I do it again, and I don't need the -A, honestly. There we go. Cut down the spam a little bit. Where did you go? There you are. So you can see that the permission is now set on the file that you guys can read it. I don't know if you actually can, because ls-ld, the current directory. Yeah, so none of you guys can actually read inside of the current directory. So sucks for you. Now, if I wanted to chmod it directly using Octal, I could say 077 like that, pwm demo-c, and you can see by using the power of Octal, 7 is 111, right? So I have set the read, write, execute, read, write, execute, read, write, execute on it. So anybody can read it, anybody can write it, anybody can execute this file. If I change it to 600, then I can read and write the file, and none of you guys can touch it. Okay. Yeah, you can't actually stat the file because you do not have stat permissions on the directory that I'm in right now. So ls-ld here. I have read, write, and execute permissions on the directory. Execute means you can stat it. Stat is a system call that returns the list of all the files within it. And so you can't actually get into my directory, and this is so you can't read the answers to the homework assignments, right? As Harlan did last year. He saw that my public HTML directory had source code in it, and it was world readable, and so he, for one assignment that had involved a web page, he pulled the source code on it. So you're doing math right now, Dolio? All right, I guess I'll have to make this more interesting. Okay, all right, so that's Unix. In general, I would recommend you guys learn as much Unix as you can, just hands down. But the reason why I'm showing you this is because this is Octal. It's not very common you'll see Octal these days, but read, write, execute, those are groups of 3 bits, and so they use Octal for it. That's the thing. Okay. Yeah. Yep. Okay, so that is binary, decimal, octal, hex. If you look at the calculator in programmer mode, you'll see those are the 4 modes we care about as programmers. But what about 2 bits? We don't care. What about 5 bits? We don't care. What about 8 bits? That's, well, sure, that's a that's a byte. Yeah. And so you can switch from quad word, double word, word, byte. So you can be in 8-bit mode, 128-bit mode, 64-bit mode, 32-bit mode, or 8-bit mode when you're doing all this stuff. So 5 times 5 is 25, times 5 again is 125, times 5 again is 113, times 5 again is 53, because it's overflowing, because we are in 8-bit world. Okay. So where will you see hex a lot? If you guys have ever done web development, colors, the image processing thing we're doing right now, color picker. So if you want to pick a color, ooh, that's an ugly shade right there. You can see that all of these numbers range from 0 to 255. So 0 to 255 sounds to me like 2 hex digits. And in fact, you can see right here, you can get a color in hex. So if you ever do web development, then web developers typically will enter colors in hex. The first 2 digits here, 4F. 4F is 64 plus 15, which is 79, right? 4F, 4 times 16, it's a 16s digit, 4 times 16, 64. And then F is 15, 64 plus 15 is 79. Okay. And so with just 6 digits, you can pick out any 24-bit color, which is usually pretty good. Sometimes you'll want to have more colors than 24-bit color. For example, HDR monitors now display, or some pretend to display, 10 bits per color. So you would need a 30-bit color instead of 24-bit color. You never realized that's how it works for colors? Or web development? Yeah, if you view the source, what's that, Control U? Yeah. Really? It's not word wrapped. Okay, that's super not helpful. Why don't you word wrap? Why are you so terrible? Okay. Okay, so if we pull up the source code for the thing, we can search it for hashtag FF maybe? No. Yeah, okay, right here. Here's the color right here. I don't know if you guys can see this. It says bottom color hashtag 282828. So 282828 is going to be a dark gray color. So if I set this to be 282828, like that, look, it's the color of the background. Yeah. The colors in web development are typically no, that's not it. Sorry, 282828. There we go. It's that color. Right. 28 in decimal is not 28 in hex. And so this is that was the background color for right here. You guys see that? And so whenever you do web development, you kind of have to know hex. It's just kind of everywhere. Any other questions about hex? If not, we're gonna move on to the homework. Nothing? Straightforward? Worst case scenario, fire up your calculator. Double check your work that way. Okay. Does that seem reasonable? .28 in decimal is 1C in hex. That's why it had 1C there. Ooh, that's a pretty shade. Okay. All right. So without further ado, let us talk about I've been using this background for a while. I do like this background. Honestly, one of my life goals is just to spend a summer in like the mountains of Japan, just have a you know, basically this. You know, just got my books there, doing some work, looking out over, you know, a valley, be like, I don't know, the Kiso Valley or something. Some morning glories there. Got some iced tea. Really should have a coaster on that, you know. Yeah, just to. I spent like, I don't know, like a week in the Kiso Valley before, but it'd be fun to spend like a whole summer there, just working. A Raspberry Pi is considered SIST when neon instructions are not given to it. They are not. Well, what Raspberry Pi? What Raspberry Pi are we talking about? This one is 4 cores. So 4 cores is MIMD, right? If you had a single core Raspberry Pi, then yeah, it would be SIST. So there's multiple kinds of Raspberry Pis. The latest one that came out is SIST. It's a $4 machine. It's got a whopping 256 kilobytes of RAM. 256 kilobytes of RAM. $4 won't run Linux like all the other Raspberry Pis. They came out with a microcontroller. So it's called the Raspberry Pi Pico, I think, which is a terrible name. Raspberry Pi Pico. It's a terrible name because Pico is already a thing in the Unix world. It's the name of the world's dumbest text editor. Yeah, so kind of issues with the name, but yeah, it's kind of like taking on the Arduino thing, because Raspberry Pis are real machines. Like Raspberry Pis are actually Linux boxes, you know, and so they're Arduinos are done for cheaper projects. Like my daughter built a camel that you can hit buttons on it, and different parts of the camel light up as part of her camel project. Last year we did a thing. Did I show you guys this? Her fish diorama. I showed it to you? Okay. So that was done using an Arduino, not a Raspberry Pi, I think. Yeah. Because if somebody stole the Arduino, I wouldn't be upset, because Arduinos are cheap as hell. The servo costs about as much as the Arduino. Okay. All right, so let's talk about the homework. So your homework, I thought about it, and I hadn't gone as far in the lecture as I wanted, so I pulled back on what I was going to do. I've split it into 2 different assignments. So one of them is going to be due this Friday at midnight, and it's very simple. The source code for it is almost in the PowerPoint presentation. And so for this one, your job is to darken an image. Okay, and so however, darkening the image and doing it correctly is only worth a C, because it's so easy. Because I've basically given you the source code for it. So all you have to do is kind of like put it in and compile it and run it. So anybody who was complaining the last assignment was too hard, this one is too easy. It's literally too easy. This will reveal to me who is attending my lectures and watching the lectures, because literally all the source code that you need is available. You can do it very, very quickly. The challenge, Rivera and I went straight from F to A+, yeah. Do we need neon to reach the fastest time bracket? Yep. Yep. Or, what else could you do? You can multi-thread it, maybe. Maybe. I don't know. Option. Okay, so, or neon plus multi-threaded, you know. I showed you guys how to make a thread, right? Just use std : thread, and you can put off 4 function calls like that. Have each function call take a different quarter of the image. With the overhead, I don't know. I'd have to benchmark it. If you do that with neon, you would probably get the highest speed possible. Use some loop unrolling, yeah. So remember how we talked about loop unrolling, how you can optimize loops away, you know, and remember branch penalties and all that kind of stuff. Yeah, it's all gonna come up here. So this is like the heart of assembly programming, right? It's like, sure, you know, you need to know how to write things in assembly, but really it's about trying to squeeze every last bit of performance out of the hardware. Okay. So, yes, if CImage, the CImage library does this, it's about 6 seconds to call the CImage darken. And if you do it in C++ yourself and turn on basic optimizations, it'll run in 0.2 seconds. If you turn on -03, it'll run in 0.04 seconds. So -03 turns on Neon, by the way. So you're competing against Neon with Neon. Because C++ is smart, the optimizer is smart, and it will enable Neon instructions on it. Yeah. Okay. And so you have to use the Kyoto JPEG file as the reference for the timing. You can't pick a smaller image. Mine ran really fast. It's 1 pixel. No, you must use Kyoto. Okay, so yeah, and so there are options available for you to blow past this, in my opinion. The honestly, the biggest bottleneck of this is just loading the thing off disk, because disk I/O is not especially fast on the Raspberry Pi. Even though it's all solid state, it's still not fast. And so the timing actually is after it's been loaded. And so your image filter is kind of a small chunk of the overall running time, right? But we're just going to pretend that all these things are already in memory, and we're just going to be processing frames of data or something like that, which could happen. Like if you write code for the video core engine, the graphics card, there is a graphics card. It's not a card. It's whatever. We'll call it a graphics card, even though it's not a card. There is a graphics card inside the Raspberry Pi that can do CUDA and things like that. So you could feasibly have that thing streaming video frames to RAM, and then you're running your filter on things in RAM in real time, and then it would be displaying them to the screen or something like that. So, being able to tweak this from like 0.05 seconds to 0.03 seconds means you've gone from 20 frames a second to 30 frames a second, right? It's a pretty noticeable difference going from 20 to 30 frames a second, right? And on 4K images, so it's on a crappy Raspberry Pi, right? Like it's pretty impressive. So assembly really is awesome. Okay, so at least you darkened 1 pixel. Okay, so let's talk about what you need to know. So the student darken code that I give you is just it returns, right? So you have to write a function. Hopefully you guys are good at writing functions by now. If we look at main.cc, you will see that here is the glue that connects your assembly to the C++. Again, it's got the extern C thing on it, so it doesn't do name mangling. And then darken. I've got some versions that'll segfault for you. I don't know what was happening here. Triple pointer to a pointer to. I don't know what's happening there. But basically, this is what you guys need to understand. So, what is an image? What is an image? An image is a 3D array of pixel data. Every pixel is 3 chars, unsigned chars, technically. Okay, that's why you see that it is taking in a array, a pointer. A pointer is an array, right? Arrays are pointers. So it takes in a pointer to the beginning of an array, and it's taking an array of unsigned chars. So it's just a bunch of RGB values. And it's going to be writing to a different array, the output array. And it knows the width and the height for the image parameters. And then what we see here is, this is not great, but it's just starting at the beginning of that array, going to the end, and dividing each value by 2, and writing that to the output array. Because for this array, it doesn't matter if you're red or green or blue, just all the values are getting divided by 2. This code darkens all values, and the reason why it darkens all values is because it is width times height times 3. 3 is because there is red, there is green, and there is blue. And so how is this array laid out in memory? Glad you asked. So there's different ways you can lay out images in memory, And the Raspberry Pi actually has support for, like, innate support for, like, especially in Neon. Like, Neon can actually support different formats, I guess, of images with instruction support. But the way that we're doing it here is it is a 3D array, and there are 3 planes. Let's draw the 3 planes kind of like this. Cool 3D graphics. Okay. First plane is called red, second plane is called green, third plane is called blue. This is the width of the image, this is the height of the image. And so if you have like a person like that, the first plane contains the red values of the image. So these will all be zeros because they're black. And then let's say that the stick figure is drawn in white. Then it'd be 255, 255, 255, 255, 0, 0, 0, 0, 0, 0, 0, 255, 0, 0, 0, 255, 0, 0, 0. And then you'll, if it's a white image, it'll be the same on the green and on the blue. Okay. So the red value will be 255, the green value will be 255, the blue value will be 255. Okay. And so if you divide all of the pixels by 2, if you half the value of all the pixels, then all those 255s for white turn into 127. All right, so it goes from full white to 50% gray. And if you add 50% gray and divide it by 2, then you get 63. Yeah, so it goes to 25% gray. And if you divide it by 2 again, it goes to 31. So it goes to 2. All right. The code darkens all, not just red. Yeah, I used to have separate channels for red, green, and blue, and I simplified it for you guys. Yeah, I used to have the reds divided by 2 and the greens divided by 2 and the blues divided by 2. Maybe I should put that back in, or maybe it's in here. Did I take it out? I must have taken it out. Yeah, like this. Okay, so this divides. So if you want to see how the red, blue, and green pixels can get pulled out separately, you can look at this. So do you see the difference in the for loop here between what we had before and what we have here? What's the difference? Yeah, so rather than looping from the start of the array to the end, because the start of the array is, you know, pixel 0, 0 in red, and at the very end it's the bottom right corner in blue. So this loop here is just looping over the entire chunk of memory. It's an entire 3D array. Remember, there's no such thing as a 3D array. All arrays are just 1D in memory. And so I'm just exploiting that for the option 1 here, right? It just starts at the very top left corner of red, runs all the way through the bottom right of red, runs through the top left of green all the way to the bottom right of green, top left of blue all the way to the bottom right of blue, and finishes, dividing all the values by 2. What I do here is I'm going from the top left of the corner to the bottom right of the corner, bottom right corner of the image, and I'm grabbing the red value, I'm grabbing the green value, I'm grabbing the blue value, dividing each of those by 2, and writing it into the corresponding spot in the output array. So again, you have to know row major ordering. Right? It's an important concept in computer science. It does a third of the iterations because it does all 3 colors in one step. Yes, this is dividing the red by 2. This is dividing the green by 2. This is dividing the blue by 2. But if you want to do something fun, you know, if you want to have fun with it and just see what happens, because you're not going to explode anything, let's multiply the green by 2 and let's divide the blue by 4. Why not? Okay. Compile, make. It is not using. I is not declared in the scope. I is not declared in the scope. That's what you get for copying and pasting the code and not running it over. There. Put curly braces around it. It's kind of important. All right, and we don't need to return. Why do we need to return? We don't need to return. Silly code. All right. Okay. So do you guys understand what stride means? Why it is width times height? Does that make sense to you guys? CAD seg faults on Kyoto.jpg. Interesting. It's possible. What is stride here? It's the height of one plane. Yeah, width times height is the width of one plane. So if you go stride to the right in the array from red, let's say you're at red pixel 5 across, 10 down, and you go stride to the right, you're now at the green pixel 5 across, 10 down. If you go stride to the right from there, you're at the blue pixel 5 across, 10 down. And so that's how you get the corresponding red and green and blue values, is just by adding stride to the current address that we're reading from. Okay. It is the size of the, it's the size of a plane. How many elements are in the plane? So if you have a 10 by 10 picture, then if you go 100 characters to the right, that is the green plane. If you go 100 characters to the right, that's the blue plane. So it's all the reds, then all the greens, then all the blues. Now, that's not always the case. Sometimes when you're doing images, you will have what's called interleaved images, in which case it goes RGB, 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 like that. And so this would be pixel 00, pixel 01, pixel 02, pixel 03. Yep, just depends. PPM, which is the world's easiest image file format. Have you guys ever seen PPM before? A PPM image file? If you ever are like getting into images, you will probably parts per million. No, that's not right. Project portfolio management. You're pretty sure that's not it either. Have you guys heard of this image format? It is the world's easiest image format. You could write a program that generates images without needing CImage and stuff like that. Here's what it is: you have a magic number, magic word, P3 to indicate it's the PPM format. You know, basically. 4x4. It is a 4x4 image. There are 255 colors, and then it is RGB, RGB, RGB. Just it's a text file. It's not even compressed. It's not even binary. Not efficient. Black, right? Black, 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 right? And so you can see that this 4x4 image is rendered like this. Okay. That's compressed as PNG. Yeah, so that is a PPM file. It's very, very not compressed at all. It's very wasteful hard drive space, but even a beginning computer science student can write a PPM exporter, PPM importer, right? Everything can read. I mean, yeah. If can a society read it? I don't know. Maybe. I'd have to check. So, yeah, it's just a standard file format, and you could write a program to generate images very easily. Magic number, size of the image, how many colors, and then it's just a series of RGB values. That's it. So it's in an interleaved format like that. JPEGs and PNGs use the plane approach. It doesn't really matter, because when you open it up in CImage, CImage puts them into an array for you. And so when you load it here, you load it there, then CImage puts it into a array of unsigned chars in planar format by default. And so I believe you can tell CImage to load it in a different format if you want. Yeah. Number of color planes. think it's frames, maybe, if you have an animated GIF. Anyhow, so, yeah. It doesn't really matter how they store it on disk, because CImage will load it in the format you like. It's templated. Like, I could change this from unsigned char to be like a float, and then all the numbers would be from 0 to 1. And so 000 is still black, but 111 would be white. And so 50% gray would be 0.5, 0.5, 0.5. And so just depending on which parameters you pass to CImage controls how it loads it. So CImage is a header-only library file that will read images. Okay, so let's try this. So we are multiplying green by 2, we're dividing blue by 4, and we are dividing red by 2. One thing you guys need to note is that if you want to call your code, student darken needs to be defined. You guys remember that from last week? If you want to call student darken your code, if you want to call your code, you must hashtag define student darken. Okay? And then down here, if hashtag student darken, then it calls yours, otherwise it calls mine. And so if you look at the makefile, in order to call your code, you want to use this one here, like that. Okay, so don't get all excited when your code works right the first time, because it's calling the C version first. So you need to switch these two. You need to switch these two things here, and I would probably put -03 into this line too, just as a heads up on that one. All right, so let's make it, and I should probably put an @ in front of this, which will silently. The hashtag in a makefile is comment, but it prints the comments out, which is kind of annoying. If you put an @ in front of it, then it silently ignores it. And you can see that it is not fast to compile. The reason why it's not fast to compile is because CImage is a gargantuan header-only library. It does not support partial compilation because everything is templated. And so what I have done, and this is something called Pimple. Program Implementation Pointer. I don't remember the acronym. But basically what you can do is you can avoid long compile times like this by passing a pointer to something. And usually this is done if you have a class. You don't need to know the actual definition of a class if you're passing a pointer, because all pointers are the same size. And so what I've done here is you only have to compile main once. And once it's compiled, it'll just sit there and call your student darken. You can recompile student darken very, very quickly. And so if we were to compile this a second time, student darken.s make, you can see it rebuilds like that. And so I deliberately did it this way, where the expensive thing with CImage is in one file, and then it just passes a pointer over to another file, and then you compile it there, and that can compile very quickly. You only have to recompile this one if you are switching between the C++ and the assembly versions of the code. So if we run this, let's run it on /public/kyoto.jpg. So the darken time was 0.03 seconds, quite good. Now how do I view it? Okay, so one thing I could do is I could use aseity and run it on output.jpg. I haven't actually run aseity on the Raspberry Pi. It looks like it's going to crash. No, it worked. Cool. Yeah, so you can see the colors are all screwed up. But if you want to get it in better resolution, aseity is actually probably pretty useful for just a quick look at what you're going to get. But really what you want to do is you want to fire up a program called WinSCP. I learned my lesson, always make sure your code works first. The most important thing that I can convey to you guys as a computer science professor is the method by which you develop, right? Which is to get a minimal working product, like a a student darken that all it does is nothing, right? And then make a version that just divides everything by, or just loops over everything, printing out every value or something like that. Just that process of developing and making sure you're staying within the boundaries and not seg faulting and stuff like that with the minimal amount of code possible, and then building up once you're confident that you're iterating over the array. And this array is too big to know if you're exactly iterating over. So I'd make like a little 5x5 image array and feed that in and print, have my assembly code just print the values. You can do that. It's okay. Just see out or see error all the values and just make sure you're getting all the RGB values you think you're getting, from the start to the finish. That incremental process of development is the most important thing I can teach you, because then you know exactly when something goes wrong, right? If you segfault on your very first for loop that's supposed to go from the start of the array to the end of the array, then you're going to look at your code and be like, oh, I'm multiplying by 4. These aren't integers. I'm going right off the end, aren't I? And so when there's only a little bit of code that could be the culprit, it's a lot easier to find the bug than after you've written a couple hundred lines of code, and so on and so forth. So, what is my password? Access denied. Okay, here we go. So WinSCP is a transfer program. It uses secure copy protocol. And if I go into ASM image, this is what I recommend you guys do when you're doing your development. Go into ASM image. And when you run your program, it's going to save it into output.jpg. So I'm going to right click on that, and I could drag this over to my desktop. I could drag it over to my desktop where you can see I've got my sea shanty thing coming along. I've got my attendance records and Wargame Red Dragon, which is a homework assignment for game development right now, where the students have to play a video game. I tell you, man, I'm a rough professor. But all I'm going to do is right-click on output.jpg, and I'm going to click on Open. And so that will transfer the image off of the server and to my computer here and view it. And so you can see that we have issues, right? We have issues. It kind of looks cool, honestly. It kind of worked out pretty well. I've actually been here in real life. This is an alley in, I think, the Gion district in Kyoto. And Michinoku. Usunaku. Yeah. So there are a bunch of restaurants and things like that. We ate there a couple of years ago. But yeah, you can see, anytime you see something like this with these like weird lava pixels and things like that, we're getting something called integer overflow. What happens is that if you make a number too big, then it wraps around, right? And so if you're doubling the amount of green, it'll work fine as long as the amount of green was from 0 to 128. But if it ever was above 128, then it wraps around to 0. So rather than being twice as high, it becomes lowered. So there are areas where it's very green because I was doubling the amount of green, and then there are areas where there's no green at all because that was the area that probably had the most green to begin with. And so you get these weird pixels and things like that. So the development process you guys should use on this homework assignment is as such. So you're going to be doing this in assembly, obviously not C++, but you're just going to come in there and modify your code. I will change that to divided by 2, save, make last a.out, which will run it with Kyoto again. This is your workflow, and again, it's going to take like 15 seconds to compile because the C image library is like 100,000 lines of code, and it re-implements large chunks of the standard library. It's kind of, I don't know, it's kind of dicey, if you're going to be re-implementing the standard library. Like you can see what penalty you have on compile time if you use a 100,000 line of code header-only library. All right, it's not snappy. It's not instantaneous, right? So. There we go. And fine. Why did that not run? Oh, I didn't run a.out. That's fine. A.out. Public Kyoto. So it runs it. The image processing time is 0.03 seconds. And so now I come back into WinSCP. I just leave WinSCP open. I right click again on, I don't double click. If you double click, it's going to open it up in Vim, which will be garbage, right? It'll look like, you know, you're opening a binary file in a text editor. Not what you want. Yeah, there you go. So you see there is a magic word right there, GIF. Not what we want. So let's close that. So what you want to do is just right click on it and choose open. And then you can see the result of your image filter. That's the workflow. You're going to modify get your image filter working, and then tweak, right? And you're going to rebuild, rerun, and then when SCP view it, and you can see the colors kind of look cool now. It's almost a sepia filter, honestly, at this point. Kind of a cool look. Okay, so yeah, all right. Just make sure you're running your code and not my code. And then on Canvas, upload what your running time is, and that will determine your points. Okay, so we need to go back to talking about Neon. I'm almost done grading the bitwise assignments. It kind of takes a while. All right. 45. 70. Demo 13, VFP. There. All right. So, in order to do anything with floats and doubles on a Raspberry Pi, you use Neon. You use the vector float processor. It's called the vector float processor because it does vectors and it does floats. And so, yeah, if you want to do vectors, use VFP. If you want to use floats, use VFP. And the old version of it was called VFP. Nowadays, it's called Neon. The 64-bit system has a different thing. By the way, your Zybooks is going to be going over this as well, but they're doing 64-bit leg. Not ARM, leg. I still, to this day, do not understand why they couldn't just teach you ARM, right? Because ARM's not hard to learn. Why make up your own non-functional dialect, you know? So, yeah, okay. So, it's taken me an arm and a leg to learn assembly. Because then they would have a good product. I don't know, like it's, you know, Patterson and Hennessy is considered the go-to book. Like they're the reference textbook. Everybody knows Patterson and Hennessy. Okay, so you can tell that you're doing a VFP instruction when there's two clues. First of all, the instruction starts with a V, right? That means it's a vector command. It's not necessarily doing a vector command. In this case, it's only loading a single number, right? It's loading into the S0 register. So the S0 register is a single word, so it's 32 bits. So that's how we know it's a float, not a double. If we were loading into D0, it'd be a double, but we're loading a float. So this is loading the address of pi into R0. Pi is down here in the data segment. So pi is a float holding 3.1415. 200 is a double, 2 is a double, divisor is a double, but pi is a float. So so we don't actually need to do LDR-F32. I think we could do that, but we don't need it. The reason why we don't need it is because Neon knows, because we're loading into a single word register, that it's going to be a float. It's 32 bits. Okay, and it doesn't care if it's an int or a float. If you screw up and load an int, it'll be an int. It's 32 bits. I don't care. Bits are bits. Okay. So pi is a float, and now we're going to convert it to 64 bits, just to show you guys how to convert between single and double precision numbers. There is a command called vector convert. Vector convert allows you to convert between ints and floats and doubles and chars and half words, and yeah. So that, not quad words. It doesn't support quad words. But you can convert between a 64-bit int and a 64-bit float, and it does the conversion for you. And so we are going to convert from the register here in S0, the single word register 0, and save the result into D4. So double word 4. And so do you remember last time how Q0 and D0 and S0 are all the same register? You notice how I didn't pick D0 here, because D0 and S0 would be the same register. And it would erase S0. Which, if I'm not using it again, probably would be fine, because I don't think I use S0 again down here. So it probably would have been fine, but it's worth having this conversation. So do you guys understand this? So you could pass in here unsigned 64-bit number, signed 64-bit int, float 64, and 16, whatever. Screw that up. So you can pass in any of the types that it supports, which are 8, 16, 32, 64-bit ints, and floats, signed or unsigned. Okay, and so that's how you convert from one format to another. Do you guys understand that? So whenever you're doing neon instructions, the neon instructions take suffixes like this, and they basically tell you what the type. It's typing. It's like it's a type system for assembly, essentially. All the stuff that we did in ARM32, none of it's typed. Bits are bits. But here it needs to know, because a quad register is 128 bits, and it can be treated as a bunch of different 8-bit numbers, or a bunch of different 16-bit numbers, or a bunch of different 32-bit numbers. And so it needs to know what it's holding so that it can keep those channels separate so they don't overflow into each other. Any questions? It's like dead silence on Discord right now. Nope. All right. So we're loading pi, which is 3.1415, and we're converting it to a double, and that's going to be held in D4. Okay. We're going to then load the address of 2. Remember, 2 is a double holding the number 2, and that is an address. Whenever you say equals something down there, that loads the address of it into R0. So R0 is a pointer to it, and then it loads the value of that pointer into D5. So using vector load again. And so that is D5. The D5 register is going to hold 2.0. And then we are going to divide. We're going to take D4, which holds pi, and divide it by 2. Look, division. There's division. Division. It exists. So if you guys want, you can do integer division in Neon. Cool. What? Yeah. Yeah, there is no division or modulus in normal ARM32. Remember, not all ARM CPUs have Neon support. It is a optional add-on. And so, but Raspberry Pis do, so there you go. So if you ever want to use division in a program, you can, it doesn't have to be a float. It could be an int. Just load an integer into there, load a couple ints up, and do a division. There you go. So rather than a float 64, you can do a I32 or a U16 or whatever, and it will do integer division for you. Just as the prophecy foretold. If you divide by 2, a shift is still faster, yeah. But we're doing floating point division, so you can't shift a floating point number and expect it to work. Shifting a bit right works fine for integers, does not work for floats. And that'll be our topic for next time. Or maybe not next time, but soon we'll learn how floats actually work under the hood. You should be learning that on Zybooks then. You can shift floats if you're a Quake developer, yeah, using the fast inverse square root thing, which is amazing. Okay, so this is how you do division on an ARM CPU. You just have to make sure your machine has a vector floating point unit, and you've got access to division. Cool. So this is computing pi divided by 2. And it needs to know what type we're doing. Are we doing 32-bit division? We're doing 64-bit? Are we doing integer division? What kind of division are we doing? That's why you have that suffix there. The .f64 means we are doing a 64-bit float division. If you don't have that there, it will not know what kind of division you want to do. Because integer division is very different from floating point division. The bits are held in completely different formats. There's the IEEE format for floating point numbers. It's completely different from 2's complement. They're not compatible. So you have to tell it what format numbers you have. Okay, this is how you move back. So this this is how you can load a value into one of these neon registers. And this is how you can move from a neon register back into a regular register. Look at this. So it's going to take the double, because we just saved the result. Pi over 2 is now in D3. A D3 is a double word. It's 64 bits. And so if you're going to move out of it into regular registers, remember regular registers are 32 bits. They're not big enough to hold a double. And so what you have to do is you have to put half of it into one register and half of it into another register. And so this is going to move, this is actually to destination registers. Remember how I said that there were some exceptions? There were some exceptions to the rule that the leftmost register is the destination register. This is one of them. And the reason for that is because it has two destination registers, because you're moving from a double word, a 64-bit number, to a pair of 32-bit numbers. And so it's going to move from D3 into R2, R3. Okay. So, yeah, okay. And so we need to get our, remember how you pass parameters to a function? First parameter goes into R0. So the first parameter goes into R0, and it gets the address of the string. And then the second parameter goes into R1, right? You guys remember that? First parameter goes into R0, second parameter goes into R1, right? You guys remember that? Not here. When you're working with 64-bit numbers, the AAPCS, the ARM, oh Lord, I forgot what the rest of the acronym means. The ARM Procedure Calling Standard, ARM, Advanced ARM Procedure Calling Standard. What's the second A for? Artificial antigen presenting cells. Well, there you go. It specifies that if you're passing a 64-bit number to AAPCS, what does the other A stand for? Advanced, maybe? If you're passing a 64-bit number, it either goes into R0 and R1 or R2 and R3. It's kind of like the alignment thing, although a little different. What does it stand for? Procedure Call Standard. ABI, right? What does it stand for? What's the acronym? AAPCS. Thanks. AAPCS. Reference this document. Title, Procedure Call Standard. Thank you. Fantastic. Yeah. ARM. It stands for the ARM Procedure Call Standard. We'll go with advanced. I don't know. I know that A means something. Okay. Yeah. All right. So the AAPCS specifies that if you pass a 64-bit number, it either goes in R0 and R1 or R2 and R3. So the first parameter here is going to go into R0, and the 64-bit number we're printing goes into R2 and R3. Okay. And if you have anything that needs to go beyond it, you have to use the stack. As you guys might have seen on the previous homework assignment, you have to push things onto the stack if you wished. If you've run out of those first four registers, then any additional parameters to a function get pushed onto the stack. Okay. So it will call print string, branch of link to printf, that prints the pi divided by 2, and then we'll do the second part. So it is going to move 8 into bytes per double, and it moves 8 into R7. It loads the address of 200, and puts that into D0. So D0 now holds the number 200. R0 holds divisor, which is 1.3. So D1, yeah, okay, sorry. D0 holds the number 200, D1 holds the number 1.3. So what are we doing? I forget. What are we doing? So we have, okay, so we have a number that's 200. We've got 1.3, and oh, I see. What we're doing is we're setting each element of the array equal to, it's like radioactive decay. Does that make sense? So the first element's going to have 200. The next element is going to have 200. Yeah, doesn't work in programmer mode. So array element 0 has 200 in it. Array element 1 has 150. Array element 2 has 118. Array element 3 has... So it's computing an exponential decay curve. Okay. Like you would do for like, I don't know, financial planning or radiation or, you know, anything like that. Anything that involves exponentiation. And so this is going to simply fill the array with like this exponential decay curve and print out the results. Bethesda's not Unix. You most certainly did not notice that with the previous assignment. Are you talking about the stack thing, Zach? Yeah, I don't think any of my homework assignments actually require you to push and pop things onto the stack. But basically what you would do is if you need to pass more than 4 parameters to a function, the first parameter is R0, then R1, then R2, then R3, and anything past that you just use the push and pop. So you just push the register onto the stack. That's it. Yeah, max was passed to the stack pointer. And so you pop it off if you need it, which you didn't. So that's why it was a good teaching moment, because it doesn't matter. Okay, so we are loading the memory address of the array. I is equal to 0, and vector store from register 4 into D0. So this is, it's going to write the value of D0 into the memory address pointed to by R4. So D0 holds 200. So this is going to write the value 200 into the first element of the array. It's doing this. So do you guys understand vector load, vector store, vector convert, vector move? So you can move between regular registers and double and quad registers. You can load from an array, you can write to an array, all the basic commands that you know and love, but there's new stuff as well, like division. Okay. And division may be something you want to do for your Darken assignment, because all you have to do for your Darken assignment is load from an array, divide it by 2, and then store it to another array. That's your whole assignment. Get a for loop going. Here's I, that's the for loop. And so here we go. Is I greater than or equal to 100? If it is, it quits. Otherwise, it comes back up to the top. So what do we need to know? So this prints the array. So it does the division up here, maybe. It writes the value. Okay. Here's the division. So it divides 200 by 1.3 and writes the result back into D0. It then writes the value into the array. It jumps back up to the top, and it keeps looping until the counter hits 100. So it adds 1 to the counter every time. So you see how you can use both R registers and D registers at the same time. It's A-okay. Everything's fine. Okay. So, yeah, that's basically what you're going to do. The example here is very close to what you're going to do with the Darken assignment. And I've also got code for Darken in the PowerPoint presentation, so let's switch over to that for the last 10 minutes of class. Love these. Love supercomputers. Cray was a genius at designing these things. So Neon Genesis Evangelion, of course, what we're learning. Okay, so yeah, here is here's the answer to the homework. Okay, so let's see. Yeah, so there's a little bit more you have to do to set it up. I'm doing a range-based for loop here. I'm not using a counter like I just used in the example I showed you. The example I showed you had I, and I would increment each time. Once I hit 100, it would quit. For this loop here, it's going to have R0 holding the start of the array, R1 holding the array that we're writing to, and R3 holding a pointer to the end of the array. So it's a range-based loop. Here's the start of the array, here's the end of the array, and it's going to loop from here to here. And so this code here loads 128 bits from the start of the array, and the pointer then moves 128 bits to the right. Cool. And then it shifts right, so it does a shift right instead of a division, because it's faster. And so it shifts all of those unsigned 8-bit numbers one to the right. You notice how it's .u8, that means an unsigned 8-bit number. So all those 16 variables. So this is loading 16 chars at a time. And then shifting, it's doing a division by 2 on 16 chars in one cycle, which is amazing if you think about it. One cycle does 16 divisions by 2. And it writes the result back into Q0. So all the values in Q0 are now half. And then it stores the results into R1 with write back. So the exclamation mark means, so we've just written 128 bits into R1, and then the pointer for R1 moves to the right. So you don't have to have a separate addition or any of that stuff. This moves the pointer after you write to it. We then compare R0 and R3. Did we reach the end of the array? If we reach the end of the array, then we're done. Otherwise, we jump up to the top and do it again. So this is a very fast loop, and it will darken your image. That's basically what you guys need to know, and that's due by Friday at midnight. So you've got 4 days to copy and paste this code. So, like I said, this assignment is a test to see who's watching these lectures. Edit your makefile. Just use your code, not my code. Okay. What is VLD1? That, I believe, means it's not interlaced. I'm just going off the top of my head. I believe that there is a version that will do interlaced loading. I don't recall though. Is that semicolon supposed to be a comma? Semicolon? Where's the semicolon? I don't see a semicolon. What do you mean by interlaced? Remember how I said that you can store an image where it's RGB, RGB, RGB? Oh. Talk about intrinsics also in the remaining time. You can also use neon intrinsics if you want to write your code, and I'll explain what that means in a second. VLD1, VLD1, VLD1. Okay, everything's VLD1. All right. Yeah, this is interlaced. So with interlaced, you have the red, the green, and the blue. It goes red, green, blue, red, green, blue, red, green, blue. In the C image,
Hi there. It's currently 13:55.
I think Mui is about to go to work.
My microphone actually.
Gotcha. That's cool.
Sorry about that.
Whereas in C image, it's all the red first, then all the green, then all the blue. Yep.
Time for work. Bye.
So this is the way it's stored in C Mui. That's all the red, all the green. That's how it is in our assignment. So that's VLD1, that's VLD3, and so that will, yeah, okay. Yeah, so it does have something to do with interleaving. Okay. Cool. Good guess on my part. Or maybe I'm just remembering it. Who knows? Okay, so here is the same code, but done differently. So this is also a vector load. It's a different vector load. It's a vector load multiple. I don't know why the registers are in the opposite order, but this will actually do this is loading into a single quad word, so this is doing 128 bits. This is actually going to load 256 bits. So it loads into D0 to D3, which is the same thing as Q0 and Q1. And then it right shifts Q0 by 1 bit, and it right shifts Q1 by 1 bit, and then it does a multiple store. All these, and notice this is in the backwards order from how normally a store works. So the store is going this way instead of the opposite way. Consistency, thy name is not ARM. So these are in the opposite order, right? These are in the opposite order. I don't know what to tell you. The exclamation mark still means right back. So when you load 256 bits, the R0 pointer moves 256 bits to the right, and then you still need to do like a comparison to see if the pointer has crossed the finish line. And there's also an edge case where, like, if your image is not exactly divisible by 256 bits, you can corrupt memory. So that might be worth checking out. And so what this is going to do, because remember when we've been talking about pipelining and things like that, you can issue 2 instructions at a time, maybe. And so you can issue both of these at the same time, and maybe this will give you better performance. It's worth checking out. So use VLD3. No, use VLD1. Use VLD1. All right, so store multiple, yeah. Okay, so if your code isn't compiling with Neon, make sure this flag is set. -M is used for machine architecture kinds of stuff. And so this tells the compiler, tells the assembler, the linker, that you have a Neon coprocessor on the current machine. So just put that in there. It should work fine. So what can you do with Neon? Vector add, you can add 16 chars together all at the same time. Vector multiply, you can add, you can multiply 8 chars and 8 chars and store the results in a 16-bit half word, which is pretty cool. Vector multiply and accumulate, do 8 chars times 8 chars plus 8 chars or 8 shorts at a time. Which is pretty amazing. You can do that in basically a cycle. Left shift, right shift, absolute value, duplicate. So if you have a value like 8 and you want to put it into all 18 of the chars, you can dupe it and it'll copy it 16 times. Convert from float stints, 32-bit float to 64-bit float, or vice versa. Sign to unsign, all that kind of stuff. You can do with vector convert. Narrowing, if you have a short and you want to turn it into a char, which is useful for image processing, right? If you do multiply, if you multiply 2 8-bit numbers together, you get a 16-bit number. And then you want to narrow it back down to 8 bits to write it, you use move, narrowing move. After you've made sure that none of the values are over 256. And we'll do watch it landing. The different suffixes, 8-bit unsigned, which is what we're doing for image processing. Signed 16-bit number, signed 32, unsigned 32, float 32. Okay. So here is vector load, vector load. So this is loading 128 bits, loading 128 bits from 2 different arrays, and the pointers move after you do the load. It's going to add those 128 bits and these 128 bits together, treating them as if they were 32-bit floats. So we've got a float array and a float array. So this is going to do 4 floating point additions in one cycle. So it's like you've loaded an array of 4 floats and an array of 4 floats, and then you add those 4 floats to each other, saving the results into Q0. We then decrement R3, which is a counter, I guess. We decrement and subtract and set. So if it ever hits 0, we terminate. Remember, counting downwards is oftentimes faster than counting upwards when you do a for loop, because you can do the subtract and set and see if you hit 0. So we subtract it, and if we have not hit 0 yet, we go back up to the top, do it again. Otherwise it breaks. Either way, whether, because this is before the branch, it will write the results into R0. So it's what this code here is doing is if you've got an array of floats and an array of floats, it's adding those arrays together and saving the results into a different array. And this will be 4 times faster than if you're doing one at a time. because it's loading 4 floats at a time and adding 4 floats at a time. Okay. So neon intrinsics, I guess we'll have to talk about that next time. It's not easier. It's not easier. Neon intrinsics allow you to do this stuff in C++. And I will allow you to do this or the next homework assignment using intrinsics if you want. That said, it's actually easier to write assembly. Neon intrinsics are for people that are scared of assembly. It's not faster. It's harder to write, honestly. I got them to run as fast as my hand-tuned code, but it was more annoying to write the intrinsics than it was to just write assembly. So, you can read about that there if you want. We'll talk more about that last time. It's not necessary. Just write it in assembly. Your code is your assignment's pretty easy. If you need to look up stuff, the demo 13 I made for you has some stuff in it. I got more floating point stuff in 14. I've got a neon intrinsics demo in 15. So, or you can just copy the code out of the PowerPoint presentation. This should not be a hard assignment. Okay. So that's it for today. And then next time, your next assignment will be doing sepia toning. So that's what the real challenge is going to be. The real challenge is going to be seeing how quickly you can sepia tone an image. Okay. But this one, I just wanted to make it easy so that you can kind of get used to neon and image processing and WinSCP and all those things that could present a barrier to you succeeding in. Okay. This one should not be hard. So that's it for today, guys. Thanks. Peace out. Stay healthy. Get lots of sleep. Eat well. And take it easy.